Okay, so the problem that we will be covering first is 2001 M3. So our topic is work, energy, and yeah. So this problem will have to do with potential energy from gravity. It has some rotational inertia stuff, and it also has kinetic energy. So yeah, so pretty much the first part is just looking at the diagram. So there's a string that connects this block over here to this apparatus, which is kind of like a spinning top. And as this block goes downwards, this top is going to unravel and then spin. So then the first part of the question says, determine the rotational inertia of the rod and block apparatus attached to the top of the pole. So the rotational inertia, I'll go to the right. So rotational inertia is I, and that's equal to the sum of all the mr squares that are on the object. So since the masses of the object are only on the right side and the left side, a distance L away, we can just sum them up. So this is going to be the m times r squared, and r is just L. And then that's for the left side, and you do the same thing for the right side. And then you end up getting 2ml squared as the rotational inertia. And that pretty much tells you how hard the object is to rotate. So for part B, it's asking us to determine the downwards acceleration of the block. So the acceleration we can find by Newton's law, which is sigma F equals ma. So to find the acceleration, that would equal the force divided by the mass. Yeah, but we can get to that part later. But yeah, so to start off, to find the force on the, sigma F equals ma, which is also equal to, what is that? Yeah, and that's equal to the force of tension minus the force of gravity. So yeah, because if you look at this block over here, the force of tension is pointing upwards while the force of gravity is pulling it downwards. Yeah, and then force of gravity is equal to mg. So we can just rewrite this as force of tension minus, and the mass is 4m, so it would be 4mg. And then this equals 4ma, because the mass is 4m again. And now, to find out how to do the rest of it, we'll have to look at the other part of we should look at the rotating apparatus as well. So if we look at the rotating apparatus, we can tell that it has a torque because it's pretty much spinning. And since this rope on the outside is pulling at a radius r from the center, the torque on this object will equal the force applied multiplied by the radius out. So the radius is just r, but the force will actually be the same as the force of tension, because it's the rope that's pulling on the apparatus and making it spin. So yeah, and this is equal to I alpha. That's just Newton's law of rotation. So by using this, we can pretty much say that force of tension equals I alpha over r. Okay, this is a T. Sorry, yeah. I'll just make that clearer. Yeah, I alpha over r. And then what we can do here is remember the conversion formula, that alpha equals a over r. So yeah, alpha equals a over r. So if we plug that into this, we'll get that. Oh, sorry, wait. I said this was going to be a t, and then I made it an I, but it's a t. I mean, yeah, t. Yeah. Yeah, so if we plug in the alpha equals A over R, then we'll end up getting IA over R squared as our force of tension. So yeah, so once again, what we wanted to solve for was this acceleration here. So what we can do is plug in this value for tension into the above equation, and then we'll get IA over R squared minus 4mg equals 4ma. If we put all the a's on one side, we get IA over R squared minus 4ma equals 4mg. And then we can take the a's out. A times I over R squared minus 4m equals 4mg. And then if we look back up here, from part A, we found that I equals 2 ml squared. So we can just plug that in when we divide. So then we'll get A equals 4 mg over those 2 ml squared. 2 ml squared over r squared minus 4m. We can multiply the top and bottom by r squared just to make it look better. So 4mg r squared over 2ml squared minus 4m r squared. And we can cancel out the m from all of these. We can divide both of these by 2, all three of them, and we end up with 2gr squared over l squared minus 2r squared. Yeah. So that's what we will get for that part. That was part C, I believe. No, sorry, part B. And then part C is asking, when the large block has descended a distance d, so when this block has gone down a distance d, how does the instantaneous kinetic energy of the three blocks compare with the value 4 mgd? So when this block goes down, what's going to end up happening is that the block that has 4m will end up having a velocity downwards after some time, after it descended that much. And then this apparatus here will also be spinning at some angular velocity. So that means that this will end up having a kinetic energy of 1/2 mv squared. Sorry, 4 mv squared. This will end up having a rotational energy, kinetic energy of what the heck? What happened? Well, that was weird. Okay. Yeah. So sorry. This will have a rotational energy of 1/2 the moment of inertia times omega squared. So if we add up the kinetic energies, they should be equal to the initial 4 mgd, which is the potential energy, because of the conservation of mechanical energy. Because, yes, we're going to say equal, because there's no other work being done on the system. All that's happening is that the potential energy from this block over here is going to be converted into kinetic energy in both the apparatus and in that same block. So they should be equal. So for the final part, we can just read it together. The system is now reset. The string is rewound around the pole to bring the large block back to its original location. The small blocks are detached from the rod and then suspended from each end of the rod using strings of length L. The system is again released from rest so that as the large block descends and the apparatus rotates, the small blocks swing outward, as shown in experiment B above. This time, the downward acceleration of the block decreases with time after the system is released. When the large block has descended a distance d, how does the instantaneous total kinetic energy for the three blocks compared to that in part C? Check the appropriate space below and justify your answer. Okay, so this system, when it's at rest, like before we let go of the 4m block, is going to just look like this. It's going to be the two masses hanging from the apparatus, and then the pulley here, and then the string is going to be coming down, and the 4M block is over here. So that's what it's going to be like at rest, but then later, once this block drops down a little, it's going to look a little different. So if this is the pulley, the 4M block is going to be further down, and then this is the apparatus, the string's going here. But as you can see in the diagram, the two blocks hanging from the apparatus will not be straight anymore. They won't be pointing straight down. Instead, they'll have an angle upwards. So since that there's an angle upwards, the block actually rose in height. This is the original height. This is the new height. So since there is an increase in potential energy of these blocks, the rotational inertia, the rotational kinetic energy will actually be smaller because we have to conserve the total energy. So since there is potential energy added, there won't be as much rotational energy. So it'll end up actually being less than before. Less kinetic energy. Yeah.